Okay, so there's this is a sample problem of a trig equation. 2 sine x equals root 2. And your task is to work out what the value of x is. Now, as it stands, we can't solve the problem directly. We're trying to work out what 2 times sine of something equals root 2, and it's tricky to figure out. So almost always in these kinds of equations, the first thing you're going to do is isolate the trig function on the left and then have some sort of value on the right, and then you can evaluate. And obviously, if you had a calculator, this would be pretty easy to do, wouldn't it? Sort of. Because remember, a calculator just gives you your first quadrant angle, not all of them. So let's just do a quick bit of manipulation. I'm going to divide top and bottom by 2, and I get sine of x is equal to root 2 on 2. Now, for a non-calculator section, the next thing you should do is consult, unless you know them, consult your table of values. Okay, I'll give you a second to do that, and you can tell me what the value of x is. And we're going to work in radians as much as possible. Ollie, what'd you get? Pi on 4. Exactly what I would expect. From your table of values, you can see x equals pi on 4. What's wrong with that? I'll give you a hint. Ollie's right. The answer is pi on 4. But, Will, there are multiple answers. Yep. Okay, so remember, when we solve an equation, we're saying what possible values of x will the following statement be true? And whilst x equals pi on 4 is true, if I substitute pi on 4 for x, I will get 2 sine of pi on 4 equaling root 2. Whilst that's true, it's not the only answer. Okay, there are multiple answers. So I want to try and model this in Desmos so you can sort of see what I'm talking about here. I could do this on the GDC as well. So if I go to the GDC and put in sine of x, oh no, you're going to keep on popping up. If I go y equals sine of x like so, there's my usual sine graph. So what I've done is I've graphed the left-hand side. I've graphed sine of x. Now, just FYI, in case you didn't see it before when I was doing it, this by default will give me a pretty squishy kind of graph because it just uses whole numbers to graph it. So if we go into the little spanner there, if we change this to something with pi in it, literally type in pi, it'll start working in pi's instead of in whole numbers. So if I go pi to 3 pi, for example, and then put the step in of, say, pi on 2, my domain is now written in pi coordinates rather than in numbers or decimals. And then for the y-axis, I know that it's just sine of x. It's only going to go between 1 and 2, so I'm just going to give myself a little bit of room. So I'll go from minus 1.5 to 1.5. Okay, that'll make it look a little bit better, and I'll step every 0.5 so I can see what's going on. Okay, so there's my graph there. It goes on forever in both directions. So this is just a snapshot of my graph, as you can see here. Okay, so that's okay, but it does go on forever. So how many solutions are there? Well, in order to work out the solutions, what I can do is I can just put in another line, and my new line is going to be the right-hand side, which is root 2 on 2. So I'm going to go square root 2 divided by 2. And this blue line, where it intersects, the points of intersection, where it intersects with the graph are possible solutions for this equation. The problem is there's infinite solutions, really. But that doesn't mean anything's a solution. It just means the number of solutions is infinite. So there's a solution, moving on, another one, another one, another one. Okay, is that okay so far? Just with, I haven't talked about the solutions themselves, just really the fact that there's lots of them when you think about it from a function perspective. Yep, any questions? All right. So really, in order to solve this, you've either got to do one of two things. Come up with some sort of statement, which is what we call a general solution, but you don't do that too. Sam, 415, you do general solutions? You don't do general solutions at least until 415, if not spec. Sam can't remember, so either can't remember or didn't do it. So, but it's definitely not methods foundation. So always then in maths methods foundation, you're going to be given a domain. So now I'm going to put one in. It'll be written like that or in domain notation. Okay, it'll be written in one of those notations. And now that you've got the domain, you need to give all possible solutions for that domain. And I'm going to take you through that now. But I just want to check, is that making sense now? Graphically, I'm going to switch back in a second, so don't stress if you haven't quite got it written down. Graphically, what I'm really doing is I'm going 0 less than, so you can use squiggly brackets to do domains in Desmos, less than or equal to 2 pi. Close squiggly brackets. And now you can see there are only two possible solutions because I've limited my domain to just this area here. Okay, unsurprisingly, quadrant 1, quadrant 2, quadrant 3, quadrant 4, all are positive in quadrant 1. Sine is positive in quadrant 2. Sine is not positive in quadrant 3. Sine is not positive in quadrant 4. So unsurprisingly, our solutions are going to be 2, one from quadrant 1 and one from quadrant 2. If, say, for example, the problem was 2 sine x equals negative root 2, then that would be negative root 2 on 2 over here, and you'd have two solutions, but they'd be from quadrant 3 and quadrant 4. See that? So it's a matter of, again, selecting the right quadrants, which will give me the solutions that I need. Now, we're not going to do it by graphing, although technically you could. It's not the usual way. The usual way would be to consider the cast diagram and solve from there. But I just wanted you to see the graphic visualization of it. Any questions before I move on? Speak now, forever hold your peace. Okay. Okay, so what does a solution look like? This is how I would do a full solution. Okay, so the first thing I would do is I would solve for the acute angle first. Okay, so full solution. The sine, now it's x we're looking at, right? So the acute angle, the base angle is going to be x hat. If sine of x hat is equal to root 2 on 2, then x hat is equal to 45 degrees, pi on 4. Now this is okay. This is why I introduced the x hat notation to start with, because I'm saying specifically the x hat is pi on 4, that acute angle, the angle between the x-axis and where the line actually is, that is pi on 4, always. Yeah? All right, the silence worries me, but I hope you're okay. Just please correct me if you're not too sure. The next thing to do, or not correct me, correct my misunderstanding if I've got it wrong that you're understanding. The next thing I do is I then use my cast diagram and I say, well, I need to know where sine of x is equal to positive root 2 on 2. So therefore, that would be here and here for sine. So I'm ticking off, I'm visualizing where my angles are going to finish off with. Is that okay? Alrighty. The next thing is to then consider what those angles would look like. Now, it needs to be, because it needs to be in these two quadrants, that means that the angle either has to be here or here, like that. It either has to be, because x hat is between the x-axis and the line, then x hat is going to be between here and here or between here and here, which means that x is going to be between here and here or all the way around. Okay? Why? Because I identify that these are the two quadrants that the angle must end up in. So therefore, x equals pi on 4. Now, in a moment, you'll get used to this, doing this stuff sort of, with practice, I mean, you'll get used to doing this stuff in your head. But the other value of x has to be, can you see? It's going to be pi minus x hat. So it's going to be pi minus pi on 4. That's why we worked out x hat. Now, what you get used to after a while is in your head continually transforming pi, 2 pi, 3 pi into a fraction. So the fraction I'm interested in is 4. So pi is 4 pi on 4. So that's equal to pi minus pi on 4 is equal to 3 pi on 4. And they're my solutions. What do you think? I'm going to do 2 more examples. Questions. Every time you ask a question, you're probably asking it on behalf of someone else as well. Okay, does that mean it's so easy you don't have to ask questions? That makes this a very good class compared to other years then, if that's the case. Okay, just making it a little bit bigger for the screen while people are writing stuff down. Okay, cool. Okay, let's have a look at example 2. For x between 0 and 4 pi, the domain is effectively quite long. Solve negative 2 cos x plus equals root 3. Now again, we are not going to touch this until we've got cos all by itself. We isolate the trig function. See if you can work a step ahead of me. If you're watching this video back, pause and have a crack at doing the next bit. Okay, did you get that? Negative root 3 on 2. Notice I've just put the negative outside. It's not root 3 on negative 2. Basically, all you're saying is that the number is root 3 on 2, and I've divided a positive by a negative, so the result is negative. Okay, good so far? Okay, next thing. Draw our quadrants. We need to find a value where cos is negative. So where is cos negative? There's 4 quadrants. Quadrant 4. Oops, sorry. Quadrant 4, Quadrant 1, Quadrant 2, Quadrant 3. So which quadrants is cosine negative? Ollie? 1, 2, 3, 4. Which ones?
S and T.
S and T. Quadrant 2 and Quadrant 3. Okay? So you're not ticking off where cosine is positive because cast gives you that. You're ticking off where you need to be. And if I've got cosine x equals negative root 3 on 2, then my angle needs to be here or here. So you're identifying where they need to be. Now, this next bit here, you can see that we've got 0 to 4 pi. Intuitively, how many answers do you think we're going to get? Keep going. It's not 0 and it's not 2. 4. Yep. Because if you can think, through one cycle, I'm going to get a solution here, I'm going to get a solution here. But then I'm going to go round again from 2 pi to 4 pi. So I'm going to get a third and a fourth solution. So I'm going to get 4 solutions all up. And my recommendation is when you've got something which goes beyond just your regular 0 to 2 pi, my recommendation is to draw a little axis for each cycle effectively. So I'm going to do this. I'm going to go one diagram, and that's going to be between 0 and 2 pi. Okay, I'll just do it with my pointer so you can see what I mean. Here's 0, it'll go to pi, then it'll go back to 2 pi. So that's one cycle. And then the next cycle will be between 2 pi and 4 pi, with this being 3 pi. Okay, so that's cycle 1 and cycle 2. So 0 to 2 pi, 2 pi to 4 pi. Is that okay? Okay, so effectively this one is going to be like that. It's going around and around again. Okay, I know where it has to stop because I identified this first. So the reason why I think these diagrams are easier is because it just compartmentalizes your thinking to one step at a time. Oh, where's it going to land? What does it look like when I split it up? So now we can just say, well, it's either going to land here or it's going to land here. And then for the next cycle, it's basically the same again. It's going to be here or it's going to be here. Okay? So that's our diagram's done. Now we're just going to work out I hope you can sort of see that in order to work this out, I'm always needing to work out the acute angle between the x-axis and the line. So I'm always needing to find hat, x hat, theta hat, whatever. So that's why my next step is to work out the acute angle. So I go cos of x hat is equal to, drop the sign because this is the acute angle, root 3 on 2, and that's equal to, consult your diagram, your table, pi on 6. Oh, oops, that's really bad. Well, way I've written that. Therefore, x hat equals pi on 6. Remember, I'm looking for the acute angle at this point. I'm not really interested yet in working on what x is. I'm just working out the acute angle. Good so far? Yes, Callum? Doesn't root 3 over 2 negative? Yes, so I'll go through that again. So the negative, remember how I said that the value of cos doesn't change, it goes between 0 and 1, but it's just whether it's positive or negative, right? So I use the negative here to show me that it belongs in either this quadrant or this quadrant, but the x hat denotes, well, what's the actual just little angle here? So I strip the sign out just for x hat, and then I'll feed the negative back to working out what the actual angle is. Yeah. Is that making sense? Thank you. Appreciate the question. Anything else from anyone? Okay, now that I've worked out x hat, let me just zoom up, and don't worry about the numbers, just worry about the thinking to start with. I've just worked out x hat, right? Pi on 6. So that means I know that the angle is going to be either theta minus x hat or theta plus x hat, either in this first cycle or in this second cycle. That's going to be 3 theta minus x hat. That's going to be 3 theta plus x hat. So I've worked out x hat so I can work out x. So that's why I say next, therefore, x is equal to, look at the first diagram, it's going to be theta minus pi on 6. Now, pi must be 6 pi on 6, so that's 5 pi on 6. Or x equals theta plus pi on 6, which is 7 pi on 6. Does that make sense?
Why is theta?
Why is what?
Why is theta pi?
There's no, I haven't met, did I say theta? Did I say theta? I'm so sorry. I'll say that again. I do apologise. X equals pi minus pi on 6. So pi minus pi on 6 because that's x hat. Or x equals pi plus pi on 6. So pi plus pi on 6 to give me 7 pi on 6. I'm so sorry. It's confusing enough already without me making it more confusing. Trust me, with practice, it becomes a real routine-oriented, this. The next two values are the next rotation on. Can you see from slide 6 that I've now got my x-axis as 3 pi, so I'm now just subtracting pi on 6 or adding pi on 6 to 3 pi now instead of pi. So that means my third solution is 3 pi plus pi on 6. So 3 pi is 18 pi on 6. 3 6s are 18. Oh, sorry, I'll keep it in order. Minus pi on 6. So that's going to give me 17 pi on 6. Yeah, 18 minus 1 is 17. Or x equals 3 pi plus pi on 6, which is equal to 19 pi on 6. And that's our 4 solutions. What you'll find is that with practice, you'll just be able to go to this final line here and go, you'll do that in your head. You'll go, okay, it's 1 less than pi, so that's 5 pi on 6. Then it's 1 more than pi, so it's 7 pi on 6. Then it's 1 less than 3 pi, so that's 17 pi on 6. And that's 1 more than pi, 3 pi, so it's 19 pi on 6. You'll do this kind of thing in your head, and then you'll just be listing them. Basically, by the time you've had enough practice. Okay? There's your 4 solutions. You might notice as well that from here, I can add 2 pi to get this one. So 5 pi plus 12 pi on 6 is 17 pi on 6. 7 pi plus 12 pi on 6, sorry, 7 plus 12 is 19 pi on 6. So they are, in fact, exactly 2 pi apart, which is what you would expect because this and this is the same spot. This is just an extra rotation, so an extra 2 pi on. Same with these 2 spots. So it's not too surprising. I kind of encourage this thinking, though, because it gets a bit tricky when the cycles aren't even, like minus pi to 2 pi and stuff like that. I'm going to do a third example, then I'm going to give you a fourth one to try yourself. Here's the third one. For x between 0 and pi, solve tan 2x equals root 3. You can pause the video. You can give you a moment to see if you can get ahead of me. What makes this different, apart from the fact it's tan? Say that, Finn? Yeah, period change. Yeah, good. So there's a 2x instead of just an x in here, and that's a period change. What impact does that have? Okay, if I said tan x equals root 3, and I said between x is between 0 and pi, how many solutions would there be? Just one, wouldn't there? Because if I drew this, there's 0, there's pi, so the angle will be between here and here, but it can't be in this quadrant because tan is negative in that quadrant, which means it must only be in this quadrant. Okay? But I've just doubled the speed at which this graph goes through. And so effectively, that's going to change the number of solutions as well. Yeah. I'm going to give you a technique which might seem a bit magical. It's not really. It's not too hard to follow, but it will absolutely give you the right answers each time. And it's acknowledging that if I'm going through twice as fast, I'm in fact going to have 2 solutions in this particular range because I'm going to be going through tan twice between 0 and pi. I'm going to be going through 2 cycles like Finn said. Okay, so, but this is the way I think is the best way to do it. It's not the only way, but I hope you like it. I'll just graphically show you what I mean. So if I go tan of x, we know that's 2 cycles from 0 to 2 pi, right? We've got 1 cycle here to pi, and then another cycle to 2 pi. So in fact, to get a single cycle of pi, I would have to just go from 0 to pi. But if I put 2x, or was it root 3, wasn't it? Okay, so if it was tan x, I'd only have one solution up there. And because the rest of it's underneath, that's all I'd get. That's a first quadrant angle. But if I make it 2x, then because it's repeating twice as fast, I end up with 2 solutions. Okay? I end up with 2 solutions. So we need to keep that in mind. How do we go about calculating 2 solutions? And we do it like this. We do a bit of a shifty. So we say let theta equal 2x. Now, what does that mean about the domain? If this is now 2x, then I am going to double the endpoints of the domain. So that is 2 times 0, and that is 2 times pi. Does that make sense? So I've shifted it, but I've also shifted the domain as a result as well. So if this said for 0 to 10 pi, it would now be 0 to 20 pi. If this said negative pi to pi, it would now say negative 2 pi to 2 pi. So what I'm doing is I'm expanding the graph's domain because I'm now graphing theta instead of x, remembering that theta is just 2x. Okay? So let theta equal 2x, then theta is between 0 and 2 pi, and we're solving for tan theta is equal to root 3. This is good news because now we've got a single value theta that we're looking at, but between 0 and 2 pi. And now the rest of it's the same for a while, and then we come back and fix it back into x's to finish with. So now we're dealing with theta. So where we've got tan theta equals positive root 3. So where is tan positive? First quadrant and third quadrant. And we've got now not between 0 and pi, but we've got between 0 and 2 pi, which means that our angle is going to be either here or our angle is going to be here. There's our 2 angles, right, for theta. So we're not going to find x hat this time, we're going to find theta hat. So the tan of theta hat is equal to what? Oh, is equal to root 3, sorry. Theta hat is therefore what? Pi on 3 on your chart. So notice that almost always, I can't think of where it wouldn't be, you'll get one of those exact values. Okay, you'll be working from one of the exact values so that you can say pi, theta hat is equal to pi on 3. So can you see from this, I've got theta hat would be one of my positions, or pi plus theta hat would be my second one, because that's pi there. So therefore, theta is equal to pi on 3, or it's equal to, I'll do it separately. Just you don't have to in your books, but I'll do it just for the notes. Or theta is equal to pi plus pi on 3. So that's equal to 4 pi on 3. 3 pi on 3 plus pi on 3 is 4 pi on 3. I'll stop there. Any questions? I haven't finished. This is just what theta is. Our goal is to work out what x is. No? So in slide 12, I'm going to wrap it up. i.e., theta is equal to pi on 3, comma, 4 pi on 3, and that is equal to 2x. Remember we said theta was 2x? But I'm not interested in 2x. What am I interested in? X, right? So how do I work out what x is? Divide everything by 2. X is equal to pi on 6, or multiply by a half, same thing. 4 pi on 6, which equals 2 pi on 3. Done. Notice that once I've done this final step here of dividing both sides by 2 or halving both sides to get my new angles here, notice that although these are between 0 and 2 pi, 0 and 360, these angles are back between 0 and pi. Okay, pi on 6 is there, and 2/3 of pi is about there. Okay, so they're back into, maybe the cast diagram's a bit tricky to look at, but they're back between these two values again. Okay, so 2/3 of pi and pi on 6 are between 0 and pi. So this final step takes our theta angles and reduces them back to our original domain. And you're done. Questions? Anything at all? I don't care how dumb you think it is. Every time you ask it, it helps clarify thinking for everyone. Whether it's like, I got lost when you put a little hat on top of an angle. I got lost when you started ticking. I don't care. Just ask the question. Yep.
I got a bit lost when you changed the domain to 2 pi.
Okay. It's almost a little trick. And maybe I'll just go forward a couple of slides to try and sort of explicitly state. What I had was a domain that was between 0 and pi. So what would the domain for 2x be? Well, if I'm doubling this, then I should double the endpoints as well. Yep. And then because I genuinely find that people find it difficult to manipulate 2x, even though it's just a thing, I tend to just replace it with theta. Yeah?
Yep.
Thank you. Does that make sense to everybody what I'm doing? Doubling. So if the question was instead tan of 3x, then this logic would flow, right? This would be x goes to 3x, 0 times 3 is 0, pi times 3 is 3 pi, and then you'd have 0 theta 3 pi. 6 pi, sorry. Yeah, 3 pi. No, I was right, 3 pi. Okay, so that's 3x. One thing else I was going to say, what was it? Yeah, so I have seen people quite handily stick with their 2x's all the way through. Tan 2x equals root 3, and then 2x hat equals root 3, therefore 2x hat equals pi on 3. It's legitimate, but I find that generally speaking, students struggle to think of 2x as a thing and 2x hat as being the acute angle, which is why I recommend the theta substitution to make it easier. Not necessary if you think, no, that makes it harder for me, I'd rather deal with 2x, absolutely fine. But I find theta hat's an easier middle step. Okay, what's the time? 22. I'm going to take you through, no, I'm not going to take you through. I'm going to give you a third example here. Fourth example? No, third example. I'm not going to go through this. I'm going to pause the video in a second, give you an opportunity yourself to have a go. This is different again because we haven't looked at sine of 2x. So you have to think about that. It's equal to minus a half. Think about that. But this is the important different bit. How are we going to deal with a domain that goes from a negative pi to a positive pi? I don't mind if you don't get there. Just have a crack. I've given you some steps here to think about. So just see what you think. And in about 10 minutes or 5 minutes maybe, I'll make a start on it just to see how you go. Okay, so 1, 2, and 3 to start with. Now, again, what makes this tricky is that I've got negative angles to deal with as well as positive angles. That makes it tricky. But I do want to point out that the process is pretty much the same. So the first thing we do is we find the new domain using theta. So the solution we let theta equal 2x. Therefore, negative pi times 2 is negative 2 pi. And pi times 2 is 2 pi. So I've got negative 2 pi to 2 pi as being my new domain for theta, my theta domain, as opposed to my x domain. Okay? Negative 2 pi to 2 pi. All right. Next thing. Work out theta hat. Sine of theta hat is equal to, remember, we dropped the sign, so it's just, we dropped the positive or negative, so it's just 1/2. And that means that theta hat is equal to what? 30 degrees? Yep, pi on 6. Good so far? Diagrams. This is the hardest bit. Let's do the easy one first, and that is we are looking for sine of theta equals negative 1/2. So that'll be in which 4 quadrants? Tan is positive, cosine is positive. So therefore, it's these bottom 2 quadrants. Now, this is the bit where we need to be very mindful of what we're doing. In the first quadrant, I've got between 0 and 2 pi. In the second diagram, I should have said quadrant, I should have said diagram. In the second diagram, I'm going to have between 0 and negative 2 pi. See what I'm doing there with my arrow? Negative 2 pi. I'm going backwards. So 0 and negative 2 pi. So that means that my angles are either going to be here or here. This is where the arrows become really important, because my next two, going to negative 2 pi, I'm going to go backwards. So it means I'm going to be here, that direction, or here, that direction. See what I mean? Okay. This is going to be negative pi here, by the way. So you've got your 4 possible angles. It's up to you to figure out what those angles would be. Solve for theta, then solve for x. I'll give you 2 or 3 minutes only to see how far you can get before I do the spoilers. When you're practiced enough, this next bit you can do just as a list, but I'm just going to spell it out a bit so that you can sort of see it in action here. So what I've got here is I'll just deal with the negatives first. I might as well, because then they're in order. So the first one's easy enough, I think. We're going from 0 down to this line here where sine is negative. So that's just negative pi on 6, 0 minus pi on 6. Okay, so the first one is negative, oh, it's the second one really, is negative pi on 6. The second one goes all the way here. Now, I'm not too sure which way you'll like to think about this. So this next one goes all the way into this quadrant here. We need to work out the value. There's 2 ways you... Okay, I'll do it this way, I think. You're going all the way to negative pi, but then you're adding on pi on 6 to get back there. So it's negative pi plus pi on 6. Oh, I keep on doing that. So negative 6 plus 1 is equal to negative 5 pi on 6. The other way I kind of look at it, and if this is more confusing, just ignore me for a second. If that's fine, just ignore what I'm saying. It's kind of like saying I'm really ignoring the negative there. It's sort of like if that's a whole pi rotation, I'm taking one away from it. So that's 5 pi on 6, but because I'm going in a negative direction, it's negative 5 pi on 6. So if that kind of is more helpful for you to think of it as taking away a pi on 6 from pi and then making it negative, you can do that. That's the hard bits done. Or theta equals, let me see now. We're looking at the first drawing now. So that's just going to be pi plus pi on 6, which is equal to 7 pi on 6. And then we've got theta is equal to 2 pi minus pi on 6, which is equal to 11 pi on 6. Haven't finished, but is that okay with everyone? And tell me if I made a mistake. So I'll just list those. So I've got i.e. theta equals, I'll list them in order as well now. So the smallest one is minus 5 pi on 6, minus 5 pi on 6, comma, minus pi on 6, comma. Then I've got 7 pi and 11 pi on 6, 7 pi on 6 and 11 pi on 6, like so. And that's what 2x equals. So therefore x is, now we're just going to multiply everything by a half. So we've got minus 5 pi on 12, minus pi on 12, 7 pi on 12, and 11 pi on 12. And they're all of them. You can see that this new one goes between negative pi and pi. It doesn't go outside our original domain. Okay. Any questions about that? We can make it trickier. We can do things like change the domain. Like that. Or just have a negative domain. Or for functions, we could have sine of x on 2 equals root 2 on 2. Same idea though. Just let theta equal x on 2 and then change the domain. Or like I was saying to you before, I could even have something like negative sine of 2x, negative 2 equals root 2, and then you have to try and manipulate it first. So we can sort of change the complexity up a little bit, but every single time it's the same idea. I wanted to get it to the point that I've got a sine of a value is equal to some sort of exact value I know, and then I need to adjust the domain potentially, and then I go about solving it. And that's basically how we do that. So for homework, please, between now and tomorrow, please have a go at doing, you can see there's a whole bunch of questions here. Have a go at doing some of them. I'm not going to check your homework for this week, so just do what you can from the textbook to make sure that you've had some practice between now and tomorrow. And that will do for today. Thanks, everyone.